Evening. Welcome to the QCIS channel. Well, on this channel, you get a daily dose of science, technology, engineering, and math. My name is Leon Jones, and tonight, talk about something that everybody is using, and it's known as artificial intelligence. Now, it can be used for a number of items, such as machine learning. Now, some of the platforms that you know of, OpenAI or Chat GPT, that's what I use. Grok, Google Gemini. There's one called Liner, and there are a number of other ones out there too. Copilot by Microsoft. Also have that one as well. And AI is becoming very, very big. Now, let's go in and let's do a little bit of defining of what AI is. And it's basically the creation of systems that can perform tasks typically requiring human intelligence, such as reasoning, problem solving, learning from data, and understanding language and images. Now, AI systems learn and improve by analyzing large data sets, and they are powered by algorithms, computing power, and of course, specialized software. Again, applications of AI include features like virtual assistants. That's right, virtual assistants, image and speech recognition, and translation services with emerging capabilities like generative AI creating new content from text prompts. Now, if we break it down, what the AI does, it enables machines to perform human-like cognitive functions such as perception, where we have AI systems using tools like computer vision can identify objects, faces, and images from sensors and camera data. Problem solving, again, using algorithms to run simulations, analyze data, find optimal solutions for complex issues. Learning, again, through machine learning. AI systems learn from data to make predictions and decisions without being explicitly programmed for every scenario. Now, you can also, if you're a computer programmer, back in those days, you had COBOL, Fortran, you still have C++, Python. You had to write code. Well, AI can write code for you. Language understanding, which is known as NLP, natural language processing, allows AI to interpret, understand, and generate human language. Reasoning, AI can evaluate information and context to form strategies, make informed decisions, and enter meaning from data. Again, that's infer meaning from data. Again, AI can evaluate information and context to form strategies, make informed decisions, and infer meaning from data. Now, the key components of AI are data. AI requires vast amounts of data to train models, identify patterns, and improve performance. Of course, here on YouTube, we always talk about the algorithm. Well, the algorithms are a set of rules that AI basically use to process data so AI can make decisions. Then there is computing power, where you have complex AI systems and the processing of large data sets that require significant computing resources. So, again, examples of AI in action. I just mentioned it earlier, virtual assistants, where you have software like Siri and Alexa that respond to spoken commands. Recommendation engines, services like Netflix that suggest content based on your viewing history. Image recognition, systems that identify and categorize features within images. And then you have what we call generative AI, AI that creates new text, images, and audio based on prompts like Chat GPT. Not only Chat GPT, Grok, Liner, Copilot, Google Gemini, and you have others. Now, as I share my screen again, let me bring up the PowerPoint. And as I bring up the PowerPoint, we deal with what we call artificial intelligence. This right here is going to break it down. It's going to give you an understanding of what I'm talking about. So, the objectives of AI, again, automation of tasks. That's automation of tasks. And what that does is reduce human effort by handling repetitive or complex processes efficiently. Enhancing decision making, provides data driven insights, predictions, and recommendations. Improving accuracy and precision by minimizing human error in critical applications. Example, medicine, engineering, and finance. Learning and adaptation. That's learning and adaptation by continuously improving performance through machine learning and experience. Problem solving capability addresses complex challenges beyond human computational limits. Machine learning collaboration, augment human intelligence rather than replacing it. Personalization delivers customized solutions, services, and user experiences. Scalability of solutions. Well, it handles large scale data and it processes across all industries. Innovation and discovery enables breakthroughs in science, technology, and industry. Cost and time efficiency. It optimizes resources while accelerating outcomes. Now, AI definitions, the study of how to make programs or computers do things that people do better. The study of how to make computers solve problems which require knowledge and intelligence. Exciting new effort to make computers think, machines with minds. The automation of activities that we associate with human thinking, decision making, and learning. The art of creating machines that perform functions that require intelligence when performed by people. Also, the study of mental faculties through the use of computational models. And of course, AI, it is the field of study that seeks to explain and emulate intelligent behavior in terms of computational processes. And it is a branch of computer science that is concerned with the automation of intelligent behavior. So if you think of AI, break it down. Thinking machines or machine intelligence, it studies cognitive faculties and does problem solving and, of course, computer science. So, what is AI? AI is a field of study, computer science, cognitive science, psychology, philosophy, linguistics, neuroscience. AI is part science, part engineering. AI often must study other domains in order to implement systems. Example, medicine and medical practices for a medical diagnostic system, engineering and chemistry to monitor a chemical processing plant. Also, AI is a belief that the brain is a form of biological computer and that the mind is computational. AI has had a concrete impact on society, but unlike other areas of computer science, the impact is often felt with only tangibility or only felt only tangentially, and that is people are not aware that system X has AI built years after the initial investment in the technology. This is again why Trump wants to invest heavily in AI. Well, what is intelligence? Is there a holistic definition for intelligence? Well, here are some definitions. So intelligence, we talk about the ability to comprehend, to understand, and profit from experience, which is a general mental capability that involves the ability to reason, plan, solve problems, think with abstracts, and we comprehend ideas in language and learn. Also, intelligence is effectively perceiving, interpreting, and responding to the environment. Now, none of us, when it comes to intelligence, know we all have our own subjective meaning of it, but what I just gave you, none of these innately tells us what intelligence is. So instead, maybe we can enumerate a list of elements that an intelligence must be able to perform. Again, perceive, reason, and infer, solve problems, learn and adapt, apply common sense, apply analogy, recall, apply intuition, reach emotional states, achieve self awareness. Now, which of these are necessary for intelligence? Which are sufficient? Artificial intelligence. Should we define this in terms of human intelligence? Well, does AI have to really be intelligent? What is the difference between being intelligent and demonstrating an intelligent behavior? Now, physical symbol system hypothesis. That's a physical symbol system. That's PSS. Basically, that consists of systems or patterns which are combinable into expressions. So basically, we're talking about processes which operate on these systems to create new symbols and expressions. So basically, consider, for instance, English as a physical symbol system. Symbols are the alphabet, expressions are words and sentences. The processes are the English grammar and parsers and dictionaries. So the PSS, which is the physical system or physical system symbol, or let's switch it around. It's the physical symbol system hypothesis. That's PSS. Say it with me. The physical symbol system hypothesis. And it states that a PSS has the necessary and sufficient means for intelligent action. A computer is a PSS. If the PSS hypothesis is true, then it should be possible to program a computer to produce intelligent actions. This is the or a goal of AI. Now, if the PSS hypothesis is not true, then you have to ask the question, what are the consequences for AI? Now, the Turing test, 1950, this is when it all started. Well, if you understand the Turing test, it was a gentleman by the name of Alan Turing. Alan Turing devised a test for intelligence called the imitation game. What that does is ask questions of two entities and it receives answers from both. So if you can't tell which of the entities is human and which is a computer program, then you are fooled, and we therefore consider the computer to be intelligent, like you have up here. You have the questions from the human and the computer and the answers. So again, which is the person and which is the computer? Solving the Turing test, ELIZA, created by Joseph Weizenbaum. The system would act like a Rogerian psychoanalyst by holding a dialogue with a person. So the dialogue would be or would consist of the doctor, ELIZA, asking questions, a human responding, and the doctor using the response to ask another question. So basically, Weizenbaum wrote the program so that it would generate the English response question based on a group of patterns. So if the user sentence matched the pattern would be used to generate the next sentence. So a more recent and much superior version is called Alice. So we're going to give you an example of ELIZA dialogue. H, men are all alike. E, in what way? H, there's always they're always bugging us about something or another. E, can you be more specific? Well, my boyfriend made me come here. E, your boyfriend made you come here? H, he says I'm depressed much of the time. E, I am sorry to hear you're depressed. H, it's true, I am unhappy. E, do you think coming here will help you not to be unhappy? H, I need help. That much seems certain. E, what would it mean to you if you got some help? H, perhaps I could learn to get along with my mother. E, tell me more about your family. Now, this is the early version of AI. Then you have the ELIZA rules. Hello, how do you do? Please state your problem. I want. What would it mean if you got? Why do you want? Suppose you got. Question soon. Do you think it's likely? Do you wish? What do you think about it? We're being a bit negative. Are you saying no just to be negative? Are you really? Perhaps I already knew you were. Why do you tell me you were? Do you often feel? What other feelings do you have? So, what ELIZA does, it has a rule to swap I and my to you and your. ELIZA pattern syntax. Well, you have pat, var, match any one expression to a variable. VAR in computer language is variable. Then you have constant or to a constant. Segment pat, match against a sequence. Single pat, match against one expression. Pat dot pat, match to first and the rest of a list. Single pat. Question is variable predicate, test predicate on one expression. Question or pat one, pat two, match any of the items or many of the patterns. That's match any of the patterns. Question pat one, pat two, match on every of the expressions. Question not pat. Match if the expression does not match. Then we have segment pat. Question variable. Match on 0 or more expressions. Question plus variable. Again, the first one was question times variable. That's when you match on 0 or more expressions. Question plus variable, match on 1 or more expressions. Double question variable, match 0 or 1 expression. Question if expression, test if expression is true. Variable, characters, variables of the form. Question name, constant, atom, symbols, numbers, and characters. This is all computer language. Now, this is the Alice demo. The Alice demo. This is known as the Alice demo. So I'm going to read it to you. Jerry, my name is Jerry. Alice, hey Jerry, here's Jerry. Do you know Turing? Alice, a brilliant and tragic figure in the history of computer science. Jerry, who else do you know? Alice, Hugh Loebner, Robbie Garner, and Steven Spielberg. Jerry, which film do you like? Alice, my favorite film is Technolus. Have you seen it? Jerry, no. I would recommend you check it out. This is what Alice is saying. Jerry is asking, what's it about? Alice, it's science fiction. Jerry, do you remember my name? Alice, your name is Jerry Seeker. So notice, unlike ELIZA, Alice has a memory that can basically handle references. Have you seen it? No, I would recommend it. So we have Alice versus ELIZA. So here's Alice talking to ELIZA. ELIZA says, I am ELIZA. Alice says, I'm very pleased to meet you, ELIZA. Alice says, how can I help you? Well, ELIZA says, how can I help you? That's right. ELIZA says, how can I help you after Alice says, I'm very pleased to meet you, ELIZA. And of course, ELIZA introduces herself as ELIZA. So as I move on, Alice says, just keep on talking to me as long as you can. That's what Alice says. ELIZA, do you wish to as long as me? Alice says, okay, I will as long as you. Eliza, do you wish to will as long as me? Do you wish to will as long as me? That's what Eliza says. Alice, okay, I will as long as you. Eliza, do you wish to will as long as me? Alice, okay, I will as long as you. Eliza, do you wish to will as long as me? Alice, okay, I will as long as you. Eliza, do you wish to will as long as me? Alice says, okay, I will as long as you. And then Eliza says, do you wish to will as long as me? See, Eliza gets stuck on the phrase, I will. Then Alice gets stuck on the same phrase. Now, how useful is the Turing test? With Eliza or Alice like rules, we can eventually solve the Turing test. It just takes writing enough rules. So, does the system understand what is it responding to? Does the system understand what it is it's responding to? No, neither Eliza nor Alice understand the text. It's just that Alice has better, more in-depth, and wider ranging rules. However, we can build a representation that models the same real world domain and knowledge base. So basically, what this is stating is the system can fill in information from the conversation. And this is sort of a database or an object with data attributes to be filled in. So basically, we can use a variety of AI representations like scripts, frames, semantic networks, and questions can be responded to by looking up the stored data. In this way, the system is responding, not based merely on canned knowledge, but on knowledge that it has learned. So, does this imply that the system knows what it is discussing? What does it mean to know something? Table lookup versus reasoning. Consider two approaches to programming a tic-tac-toe player. Again, consider two approaches to programming a tic-tac-toe player. Solution one, a pre-enumerated list of best moves gives the board configuration. Solution two, rules or a heuristic function that evaluate a board configuration and using these to select the next best move. So basically, solution one is similar to how Eliza works. This is not practical for most types of problems. Consider solving the game of chess in this way or trying to come up with all of the responses that a Turing test program face. Solution two will reason out the best move. So given the board configuration, it will analyze each available move and determine which is the best. So such a player might be able to explain why it chose the move it did. So we can basically potentially build a program that could pass the Turing test using table lookup, even though it would be a large undertaking. Also, could we build a program that can pass the Turing test using reasoning? Even if we can, does this necessarily mean that the system is intelligent? And we have slot filling. Robert Schenck created the script representation. The script describes typical sequences of actions and actors for some real world situation. A story, say a newspaper article, is parsed and slots are filled in. SAM, which is a script applier mechanism, uses the filled in script to answer questions. The script provides the knowledge needed to respond like a human and thus solve the Turing test. And this is Schenck's restaurant script. Here's what it looks like right up here. So then we have the Chinese room problem from John Searle, philosopher, in an attempt to demonstrate that computers cannot be intelligent. The room consists of you, a book, or storage area, which is optional, to a mechanism for moving information to and from the room to the outside. So we have a Chinese speaking individual that provides a question for you in writing. You are able to find a matching set of symbols in the book and storage and write a response also in Chinese. Chinese room, an analogy for a computer. You have your user, then you have your input, output, pathway, bus, output. So note, Searle's original Chinese room actually was based on a script that was implemented in Chinese. Our version was just a variation of the same thing. This is your symbol applier mechanism. That's your SIM. What is your CPU? That's your central processing unit. Now, in every computer, that's your tower. Now, Searle's question. You were able to solve a problem of communicating with the person user, and thus the room passes the Turing test. But did you understand the Chinese messages being communicated? Since you do not speak Chinese, you did not understand the symbols in the question, the answer, or the storage. So can we say that you actually used any intelligence? So basically, by analogy, since you did not understand the symbols that you interacted with, neither does the computer understand the symbols that it interacts with. We're talking about input, output, program code, and data. So Searle concludes that the computer is not intelligent. It has no semantics, but instead is merely a symbol manipulating device. The computer operates solely on syntax, not semantics. Now, he defines two categories of AI. Searle defines two categories of AI. You have strong AI, that's the pursuit of machine intelligence. Then you have weak AI, the pursuit of machines solving problems in an intelligent way. Again, Searle defines two categories of AI. The pursuit of machine intelligence, that's your strong AI, and your weak AI is the pursuit of machines solving problems in an intelligent way. But computers solve problems. We can clearly see that computers solve problems in a seemingly intelligent way. Now, the question is, though, where is the intelligence coming from? Well, there are numerous responses to Searle's argument. The system's response. So the hardware by itself is not intelligent, but a combination of the hardware, software, and storage is intelligent. Now, in a similar vein, we might say that a human brain that has no opportunity to learn anything cannot be intelligent. It is just the hardware. Then we have the robot response. A computer is void of senses and therefore symbols are meaningless to it. But a robot with sensors can tie its symbols to its senses and thus understand symbols. Then we have the brain simulator response. So if we program a computer to mimic the brain, example with a neural network, then the computer will have the same ability to understand as a human brain. Brain versus computer. Now, in AI, we compare the brain or the mind and the computer. Our hope, the brain is a form of computer. Our goal, we can create computer intelligence through programming, just as people become intelligent by learning. But we see that the computer is not like the brain. The computer performs tasks without the understanding of what it's really doing. Again, the computer will perform tasks without understanding what it's doing. Now, does the brain understand what it's doing when it solves problems? That's a yes or no question. And it can be subjective. Then we have symbol grounding. One problem with the computer is that it works strictly syntactically. Then we have our opcode 1001101. It translates into a set of microcode. Instructions such as move IR to MAR signal memory, read move MBR to AC. So basically, there is no understanding. So you can put in X equals Y plus Z. It's meaningless to a computer. Why? Because the computer doesn't understand any addition. It just knows that a certain opcode means to move variables to the adder and move the result elsewhere. So do you know what addition means? So if so, how do you prescribe meaning to plus? How is this symbol grounded in your brain? Can a computer similarly achieve this? So can the computer act as if it were a brain? In other words, can a computer have a similar achievement to the brain? Now you recall Shank's restaurant script. Does the computer know what the symbols waiter or P-trans represent? Or does it merely have code that tells the computer what to do when it comes across certain words in a story or how to respond to a given question? So we have two AI assumptions. We can understand and model cognition without understanding the underlying mechanism. That is the model of cognition that is important to the physical mechanism that implements it. Again, when we understand and model cognition without understanding the underlying mechanism, I just say it's the model of cognition that is important, not the physical mechanism that implements it. Now, if this is true, then we should be able to create cognition or mind out of a computer or brain or even other entities that can compute, such as a mechanical device. This is the assumption made by symbolic AI researchers. Now, of course, cognition will emerge from one proper mechanism, and that is the right device fed with the right inputs can learn and perform the problem solving that we as observers call intelligence. So, as a result, and this is cognition, it will arise as the result or side effect of the hardware. Now, this is the assumption made by connectionist AI researchers. So notice that while the two assumptions differ, neither is necessarily mutually exclusive, and both support the idea that cognition is computational. And that is true even when we utilize our brain. We could come from two different angles, but arrive at the same answer. Now, problems with symbolic AI approaches: scalability. It can take dozens or more man years to create a useful system. It is often the case that systems perform well up to a certain threshold of knowledge, approximately 10,000 rules, after which performance, accuracy, and efficiency degrade. Then we have our brittleness. That's right. I usually use brittle when it comes to civil engineering metals, but here with AI, we use brittleness. And brittleness is basically most symbolic AI systems are programmed to solve a specific problem, move away from the domain area, and the system's accuracy drops rapidly rather than achieving a graceful degradation. Now, this is often attributed to the lack of common sense, but in truth, it is a lack of any knowledge outside the domain area. And that is, again, when we look at the brittleness, most system, we deal with most of the system AI or the symbolic AI, and it's the degradation. So brittleness, again, I go over it. It's when we have most symbolic AI systems that basically programmed to solve a specific problem, but move away from the domain area and the system's accuracy drops rapidly rather than achieving a graceful degradation. Again, this is often attributed to the lack of common sense, but in truth, it is a lack of any knowledge outside of the domain area. So, no or little capacity to learn, so performance accuracy is static. Now, what do I mean by static? Well, in civil engineering or mechanical engineering, you take a course called statics. So when something is static, it's stationary. It doesn't move. This is why in statics, in order to solve a statics problem, everything must equal zero. So basically, with this computer language, it's talking about you have performance and capacity to learn. Well, if you have a little capacity to learn and you have accuracy, well, what happens? They're both, when you put them together, they're both static. There's no movement. So then you have a lack of real-time performance. Now, problems with connectionist AI approaches. No memory or sense of temporality. So the first problem can be solved to some extent. The second problem arises because of a fixed size input, but leads to poor performance in areas like speech recognition. So basically, learning is problematic. Learning times can greatly vary. And overtraining leads to a system that only performs well on the training set, and undertraining leads to a system that has not generalized. And you have no explicit knowledge base. So there is no way to tell what a system truly knows or how it knows something. And then you have no capacity to explain its output. Explanation is often useful in an AI system so that the user can trust the system's answer. Now, I've actually run a few answers in AI. I've run it with Copilot. Course Hero has AI, Grok, Liner, and for the most part, all of the programs were right, but I did get different answers when I use Course Hero, and even when you're putting something in the address bar in Google, you might get a different answer as well. So all AI is not consistent with giving you the same answer. It is not. Now, AI is like a computer. The computer is only going to spit out what you put in it. That's what people need to understand. So now we get to the real deal. So what does AI do? Well, most AI research has fallen basically into two categories. So you select a specific problem solve, you study the problem, perhaps how humans would solve it, and you come up with a proper representation for any knowledge needed to solve the problem. You acquire and codify the knowledge. You build a problem-solving system. And then you select the category of problem or cognitive activity. Example could be learning, natural language, or understanding. And then you theorize a way to solve the given problem. And then you build systems based on the model behind your theory as experiments. Then you modify as needed. So when you put all that together, both approaches require one or more representational forms of the knowledge, some way to select proper knowledge, and that is search. So what is search? Well, we define the state of the problem being solved as the values of the active variables. Again, search, we define the state of the problem being solved as the values of the active variables. And basically, this will include any partial solutions, previous conclusions, user answers to questions, etc. So while humans are often able to make intuitive leaps or recall solutions with little thought, the computer must search through various combinations to find a solution. To the right is a search space for tic-tac-toe. And that's the game of tic-tac-toe. And that's what it looks like. Now, search spaces and types of search. Search spaces and types of search. Now, the search space consists of all possible states of the problem as it is being solved. So, a search space is often viewed as a tree and can very well consist of an exponential number of nodes, making the search process intractable. Search spaces must be pre-enumerated or generated during the search process. So some search algorithms may search the entire space until a solution is found, while others only search parts of the space, possibly selecting where to search through a heuristic. Now, when you are, and I'm going to mention this word because I've used it in courses. It's called this. You're going to see that term again in this PowerPoint. When you saw that tic-tac-toe game, how everything looked like a tree, well, the computer was going through the decisions on how the moves were made in tic-tac-toe. Well, that tree is known as a decision tree. And you see a lot of decision trees in linear programming. So you could be in a operations management or management science. That's where you find decision trees. So getting back to this PowerPoint, search spaces do include game trees like the tic-tac-toe game. Decision trees, I just mentioned that. Combinations of rules to select in a production system. Networks of various forms. And then you have other types of spaces. Now, if you look at what is on this PowerPoint, you have a decision tree. Now, something that computer language has as well, you don't have it here, you have a flow chart. Well, a decision tree is similar to a flow chart. You're going to have yes or no. You're going to be asking questions, if then questions. You might try to prove if something is true or something is false. But this is how decisions are made. And this is how AI does the talking. What I'm giving to you right now is the breakdown of how AI actually works. Most people get in there and they can type some, but they don't know really what they're typing. So you're asking the computer, whatever you put in, you're going to get an output. So that's why you carefully put in your information. And one thing about AI, you can put in information and ask for detail, and it will give you detail. In fact, I've put in information and it gave me sources. And that's more of the decisions. You start with 0, 0, then you go with 4, 0, 0, 3. Now, what are these? Ordered pairs. That's what in mathematics, these are ordered pairs. 0, 0 is an origin. And generally, these ordered pairs are in 2 dimensions, x and y. So your x value here is 4, y value is 0, x value 0, and 3. And then you go down and you have numbers. And what are they asking you to do? You have decisions. What is this decision tree doing? That's the question to ask. And you look at the execution. What are you trying to come up with as a solution? Now you have search algorithms and representations. So you have breadth first, depth first, best first, which is a heuristic search. Then you have A star or A asterisk, hill climbing, limiting the number of piles, minimax, alpha beta pruning, adding constraints, genetic algorithms, forward versus backward chaining, and we will study the various forms of representation and uncertainty when I do another one of these videos because you also have different kinds of knowledge. And knowledge, you need to understand it needs to be represented. And I just mentioned one earlier. Production systems of some form are very common. I just mentioned if then rules, predicate calculus rules, operators. Well, what's an operator? Your operators are your plus, minus, division, and your asterisk for your multiplications. And then you have your other general forms that include semantic networks, frames and scripts, knowledge groups, models, cases, agents, ontologies. So people believe that AI is something new. Well, I'm going to give you a brief history of AI, 1950s. Computers were thought of as electronic brains. The term artificial intelligence was coined by John McCarthy. John McCarthy also created Lisp in the 1950s, and that's the late 1950s. Alan Turing defines intelligence as passing the imitation game, the Turing test. AI research largely revolves around toy domains. So computers of the era didn't have enough power or memory to solve useful problems. Problems being researched include games, example checkers, primitive machine translation, Block's world, planning and natural language understanding within the toy domain. Early neural networks research, the perceptron, and automated theorem proving and mathematics problem solving. Then the 1960s, AI attempts to move beyond toy domains. Syntactic knowledge alone does not work. Domain knowledge required. So early machine translation could basically translate English to Russian. The spirit is willing, but the flesh is weak becomes the vodka is good, but the meat is spoiled. Again, the early machine translation could translate English to Russian. The spirit is willing, but the flesh is weak becomes the vodka is good, but the meat is spoiled. So the earliest expert system created is known as Dendral. Perceptron research comes to a grinding halt when it is proved that a perceptron cannot learn the XOR operator. So basically, US sponsored research into AI targets specific areas, not including machine translation. So Weizenbaum creates ELIZA to demonstrate the futility of AI. Then we get to the 1970s. So there is history with AI, and I'm giving it to you right now. Again, AI is not new. It just evolved from the 1950s. So here in the 1970s, AI researchers addressed basically real world problems. AI during the 1970s, AI researchers addressed real world problems and solutions through expert knowledge-based systems, medical diagnosis, speech recognition, planning and design, uncertainty, handle, implemented. So you had fuzzy logic, certainty factors, Bayesian probabilities. AI begins to get noticed due to these successes. AI research increased. AI labs are sprouting up everywhere. AI shells and tools were created. AI machines available for Lisp programming, criticisms. AI systems are too brittle. AI systems take too much time and effort to create. AI systems do not learn. And we get to the 1980s. Funding dries up, leading to the AI winter. Too many expectations were not met. Expert systems basically took too long to develop, too much money to invest. The results did not pay off. Neural networks to the rescue. Expert systems took programming and took dozens of man years of efforts to develop. But if we could get the computer to learn how to solve the problem, That was what they wanted to do. And we had multi-layered back propagation networks that got around the problems and perceptrons. Then the neural network research, heavily funded because it promised to solve problems that our symbolic AI could not. Again, the neural network research, heavily funded because it promised to solve problems that the symbolic AI could not. So by 1990, funding for neural network research was slowly disappearing as well. Neural networks had their own problems and largely could not solve a majority of AI problems being investigated. Panic. So, how can AI continue without funding? 1990s, a life. The dumbest smart thing you could ever do is staying alive. We start over. Let's not create intelligence. Let's just create life and slowly build towards intelligence. A life is lower, is a life basically is a lower bound of AI. A life includes evolutionary learning techniques, genetic algorithms, artificial neural networks for additional forms of learning, perception and motor control, adaptive systems, modeling the environment. And let's disguise AI as something new. Although it wasn't new, it's being disguised as something new. And they did it so they can get some funding. But the problems, genetic algorithms are useful in solving some optimization problems and some search-based problems, but not very useful for expert problems. Perceptual problems are amongst the most difficult being solved. Why? Because it's a very slow process. And finally, today, we call it the new old. Look around. Who is doing AI research? Well, by their own admission, AI researchers are not doing AI. They are doing intelligent agents, multi-agent systems, collaborations, ontologies, machine learning and data mining, adaptive and perceptual systems, robotics, path planning, search engines, filtering recommendation systems, and areas of current research interest. NLU information retrieval, speech recognition, planning, design, diagnosis, and interpretation, sensor interpretation, perception, visual understanding, robotics, approaches, knowledge base, ontologies, probabilistic, HMM, Bayesian nets, neural networks, fuzzy logic, and genetic algorithms. And once again, when we basically talk about AI, which is artificial intelligence, we're basically talking about the creation of systems that can perform tasks typically that require human intelligence, such as reasoning, problem solving, learning from data, and understanding language and images. AI systems learn and improve basically they analyze large data sets and they are powered by algorithms, computing power, and specialized software. Applications of AI include features like virtual assistants, image and speech recognition, translation services with emerging capabilities like generative AI creating new content from text prompts. So basically, I just gave you a history of AI and what AI really is. Now, again, you have different platforms, Copilot, you have Gemini by Google, Alexa, Siri, Grok, Liner. You even have AI that can actually take something that was AI generated and it can make it into something that's human. That's what AI can do. AI can also do mathematics. but it's all about the computer language because AI is a mixture of machine learning, data, computer language. And you remember something when we talk about computers, it's basically you as the human being, you still control that machine because you're telling that machine what to do. And that AI is getting that data from the source. That's why it can do translation, but it understands data. And you have Chat GPT and Grok. A lot of people are utilizing AI. But you need to know what AI is, know the history of AI, and you need to know what AI does. And that concludes this topic on artificial intelligence. If you like what I just presented, please comment, share, and subscribe. And if you're looking for some political content, check out my main channel, the 411 Talk Zone Radio Show channel. Now, here's where you can find me on YouTube. For the 411 Talk Zone Radio Show channel, you can find me on YouTube, Rumble, X, formerly Twitter, and Truth Social. And for the QCIS channel, you can find me right here on YouTube, X, formerly Twitter, and of course, LinkedIn. And I'm working on making my days current. I'm actually going back into the middle of the week, which I'm going to work on that because it's not as many people that come on during the middle of the week. But if I have to, I'll go through the weekends as well. But regardless, the bottom line is I'm going to give you this information, particularly from this channel, the QCIS channel. On this channel, you get a daily dose of science, technology, engineering, and math. Until next time, my name is Leon Jones. I want you all to have a wonderful and gracious evening.